Dear student, we're here once again. I want to take your physics, and the topic of today is equilibrium of coplanar forces and stability. Specific objective. At the end of the lesson, you should be able to state the conditions for the equilibrium of parallel coplanar forces. State the condition for the equilibrium of non-parallel coplanar forces. Then define center of gravity. Then state the relationship between center of gravity and stability. Then list the types of equilibrium and give examples of each. Now, parallel coplanar forces. First of all, what is a coplanar force? Okay, so we say coplanar forces are forces that lie in the same plane. So when two or more forces lie in the same plane, we say that they are coplanar. Whether they lie on the same horizontal plane or the same vertical plane, they are said to be coplanar forces. Now, what of the parallel forces? You all know what we mean by parallel. So we say parallel forces are forces whose lines of action are all parallel to one another. When the lines of action of the forces are parallel, so you know that such forces are said to be parallel. So now we say that a parallel coplanar forces are forces whose lines of action are parallel to one another and they are all acting on the same plane. So we now say that when a body is in equilibrium under the action of several forces, it does not move or rotate. So it will just be stable, be in equilibrium without movement, no tilting, no rotating. It will just be stable. Now, let us look at the condition for the equilibrium of parallel coplanar forces. Then look at the forces. Then we say the algebraic sum of all the forces acting on the body in any direction must be 0. So in other words, we say the sum of upward forces must be equal to the sum of downward forces. So we can just say that all the forces acting in one direction, the sum is equal to the sum of all the forces acting in opposite direction. That is what this first condition is telling us. Then we look at the moment. So we say the algebraic sum of all the moments of all the forces acting about any point must be 0. So in other words, we say the sum of clockwise moments about any point must be equal to the sum of anticlockwise moments about the same point. So this point must be noted. It must be about the same point in consideration. Okay? Now, let us look at non-parallel coplanar forces. There are some cases whereby several forces are acting on a body to keep the body in equilibrium. So, we say that when we have such non-parallel coplanar, for instance, you have some vertical forces and some horizontal forces. So you know the vertical forces, all the vertical forces are coplanar to one another, while all the horizontal forces are coplanar to one another. But when we consider all of them in general, we say that they are non-parallel coplanar forces. Okay? So now we say the non-parallel coplanar forces can be easily resolved into horizontal and vertical components. So they can then be considered as two sets of parallel forces perpendicular to each other. Okay, let's look at the condition. The condition for the equilibrium of non-parallel coplanar forces. Now we look at the forces. We say the vector sum of all the forces acting on the body must be 0. Please take note, we say vector sum. In the parallel coplanar we say algebraic sum, but here we say vector sum. So we are going to discuss later, maybe in our Zoom class we discuss the difference between the algebraic sum and the vector sum. Then we solve questions to show them. So now we say, in other words, algebraic sum of the components of forces acting on the body in any two perpendicular directions must be 0. So in this case, we are talking about components. So because we say we are resolving the forces in two components. So we now say the algebraic sum of all the horizontal components must be 0. That's why we have sigma fx is equal to 0. Fx means all the forces acting in the x component. That's the horizontal component. Then again, the algebraic sum of all the vertical components must be 0. So the vertical component, that is sigma fy, is equal to 0. Okay, then the moment. We say the algebraic sum of the moment of all the forces about any point in the plane must be 0. So that is the sum of clockwise moments about a point must be equal to the sum of anti-clockwise moments about the same point. So that's why we have sigma m0 is equal to 0. So that is to tell you we consider a point 0. So the algebraic sum of all the moments about that same point will be 0. Okay? Now let us look at the equilibrium under the action of three non-parallel forces. So where the three forces are not parallel, but they act on a body. So we say if three forces act on a body to keep it in equilibrium, we can use a special method of dealing with such problem. So firstly, one condition is that the three forces must lie in the same plane. And the next one is that their line of action must intersect in a common point. Then the third condition is that the vector representing the three forces can be arranged to form a closed triangle with sides respectively parallel to the direction and proportional to the length, to the magnitude of the forces. So now what we are saying here is that if the three forces are represented in magnitude and direction by the three triangles, the sides of a triangle, then we now say the length of each side of the triangle will be proportional to the magnitude of the force. So that means the bigger force will be represented with a longer line, a longer side of the triangle, while the smaller force will be represented with the smaller side of the triangle. In this case, all the forces must maintain their direction. Okay? So now, when we have such case, In order to handle such case, we apply what we call Lame's theorem. Lame's theorem is talking about, he said that if three forces are in equilibrium, then Lame's theorem is just a version of sine rule. So it relates force to the angle between their directions. So the Lame's theorem states that if three forces acting at a point are in equilibrium, then each force is directly proportional to the sine of the angle between the two other forces. Okay, so look at the diagram. So in this diagram, you see the three forces A, B, and C are in equilibrium. So you see that the force A is directly proportional to the angle alpha. The angle alpha is the angle between force B and C. Then force B is directly proportional to the angle beta, which is between A and C. While force C is also directly proportional to angle gamma, which is between A and B. Now, with the knowledge of vector and triangular vector, you know we can represent these three forces in a triangle. So when we represent it, we now apply the Lame's theorem. So now let us go to the quantitative part of the theorem. Now we say let P and Q be three forces and ABC is a triangular force. Okay, if the angle between P and Q is theta, then angle ABC is equal to 180 minus theta. Then angle BAC will be 180 minus alpha, and angle ACB is 180 minus beta. You know, here we have represented the vector or the forces in a triangle. So now we apply the sine rule, which is this Lame's theorem. Now say that AC is over sine 180 minus theta is equal to AB over sine 180 minus alpha is equal to BC over sine 180 minus beta. So you know sine 180 minus theta is the same thing as sine theta. Likewise, sine 180 minus alpha and beta. So therefore we have P over sine theta is equal to Q over sine alpha is equal to R over sine beta. This is because P, Q, and R are proportional to the side of the triangle. So now we are going to, we are going to solve examples on this Lame's theorem later for proper understanding. Now we say that Lame's theorem is used mainly when the three forces are known, the three angles, sorry, when the angle between the three forces are known. That is when it is best used. Okay? Now we look at the center of gravity. We say any object such as stone may be regarded as made up of a large number of tiny particles. You know, stone is a matter, and matter is made up of what? The tiny particles. The tiny particles is what? The atom. So now we are talking about those tiny particles. Let's say that those tiny particles, they are of equal masses. Each of them has mass m, and each of them is pulled by the same force. That force is the weight, which is what? mg. That is the force of gravity on the particle. So therefore, the earth pull on the object is made up of what? A large number of equal parallel forces. Since all of them are pointing downward, they are all parallel. So if you check, so now we now say that these parallel forces have resultants, the total sum, mg plus mg plus mg plus, and so on till we have the number of particles that make up that mass, and that will be equal to m, capital letter mg, where the capital letter M is equal to the summation of the masses of all the particles. Look at the diagram showing such. You see, we give example that this object, this is a rigid shape. This rigid shape, we assume that it is made up of what? The several particles acted upon by downward forces, mg, mg, mg. So that's why we say that the force concentrating at the center, that center where it is concentrated is the center of gravity, and it is denoted by G in that diagram. So we represent it with capital letter mg. Remember, we said that capital letter M is the summation of all the masses of the particles. Okay, now let us look at positions of center of gravity of some regular shapes. Number one, we said the center of gravity of a uniform beam is the midpoint of the length of the beam. Please take note of the word uniform. Once the beam or a rod is uniform, the center of gravity will be at the middle of it, the center. But when it is not uniform, so please don't assume it is at the center. Okay? Then number two, the center of gravity of a circular object is the center of the circle. Provided you know the circle is a uniform circle. We are talking about a uniform circle. Okay? Now the center of gravity of a uniform ring is at the center of the ring. Then number four, the center of gravity of a uniform square or rectangle is the point of intersection of their diagonals. Then number five, the center of gravity of a uniform triangle is the point of intersection of their median. So this is the position of center of gravity of some uniform shapes. So whenever you see a uniform shape, you don't need anybody to tell you the position of the center of gravity, because it has already been stated here. Okay? Now, okay, so we look at types of equilibrium. Types of equilibrium. So we said that there are three types of equilibrium. Number one, stable equilibrium. Number two, unstable equilibrium. And number three, neutral equilibrium. Now we start with stable equilibrium. So a body is said to be in stable equilibrium when on receiving a slight displacement, it tends to return to its original position. I want to give an example. For instance, you are sitting on a chair. If you suddenly pull the chair up, allow the chair will do what? Fall back to its original position, especially when the chair is resting on a horizontal surface. This is because this chair is stable, is in a position of stable equilibrium. So we say that this is because the line of action of its weight passes through the base. Please take note, this is a very important point. So anybody that is in a stable equilibrium, the line of action of its weight always lie on the base. It passes through the base. So we say that a body with large base and low center of gravity is always stable. So it is for this reason that racing cars have low center of gravity and wide tires to give them high stability. So if you look at the racing car, they are very close to the ground. The reason why they are very low like that is to do what? To ensure that the center of gravity is very low. And if you see them also, their tires are very, very wide. This is to make sure that their base is wide. So any slight displacement, the car will return to its original position. So examples of bodies in stable equilibrium. We say a cone resting on its base. When a cone rests on its base, even a cylinder resting on its base is in stable equilibrium. A ball in the middle of a ball. So if you put a ball in the middle of a ball, if you push the ball, it will go back to the midpoint of the ball because it is what? Stable. I will also say a chair standing on a flat surface. Even the desk you sit, when it is resting on a flat surface, it is stable. Because any slight displacement, it will return to its original position. Okay, then unstable equilibrium. Now, a body is said to be in unstable equilibrium when on receiving a slight displacement, it tends to move on further away from its original position. Now, this is because the line of action of its weight lie outside the base. So once the line of action lie outside the base, the body is said to be unstable. So we now say a body with a small base and high center of gravity is usually unstable. So consider a situation where somebody is standing with one leg. If you are standing with one leg, there is a slight displacement. Let's assume somebody push you, you will just fall. You will turn to a new position, that is falling because you are unstable. So by the time you stand with one leg, the center of gravity, your center of gravity will go up, thereby increasing the potential energy, so making you to be more unstable. That is why some of all these big lorries, when they are overloaded, you see that the center of gravity, their center of gravity will be very high. At that point, they will be unstable. So that's why when they are moving and there is any slight displacement, maybe the entire porthole, which will just displace them small, they will fall because they will move further away to a new position because they are unstable. Okay, so examples of body that are unstable is a cone resting on its vertex. So when a cone rests on its vertex, any slight pushing, the stone will fall to a new position. Also, when an egg standing on its pointed end. Also, a ball resting on a slopy ground. You know, a table, or let's say a chair that is formerly stable can be made to be unstable by displacing when you displace the stone, the chair in such a way that the line of action lie outside the base. The chair will now become unstable and it will have a tendency to do what? To move further away from its original position to a new position. In that case, it is unstable. Okay, we now go to the third type of stability or equilibrium, which is neutral equilibrium. Now, a body is said to be in neutral equilibrium when on receiving a slight displacement, it tends to come to rest in its new position. Here, the center of gravity of the body remains unchanged as it comes to the rest. For instance, consider a cylinder resting on its curved surface or a cone resting on its curved surface. When you push it, it will just roll and come to rest. As it is rolling, the center of gravity remains unchanged. It doesn't change. So in such a case, the body is said to be in neutral equilibrium. So we give an example here, a cone resting on its curved surface. Also is a ball rolling on a horizontal floor. They are all said to be in neutral equilibrium. Okay, now look at before the assignment. In summary, we say that a system of forces are said to be coplanar when they are acting on the same plane. So a system of parallel forces acting on the same plane are called parallel coplanar forces. And we say that for coplanar forces to be in equilibrium, for a body to be acted upon by the several forces that are coplanar and parallel to be in equilibrium, we say the algebraic sum of all the forces about any point will be 0. That means the sum of upward forces will be equal to the sum of downward forces. We also say the algebraic sum of all the moments of forces about any point will be 0. That means the total clockwise moment will be equal to the total anti-clockwise moment. But for non-parallel coplanar forces, we say the vector sum of all the forces acting on the body will be 0. That means the algebraic sum of all the horizontal component forces will be equal to 0, and algebraic sum of all the vertical component of forces will be equal to 0. We also say the total clockwise moment is also equal to the total anti-clockwise moment. Then we also say that the center of gravity is a point where the resultant weight of the object acts. That is the center of gravity. And we gave the center of gravity of some uniform shapes. Then we also mentioned the 3 types of equilibrium, which is stable, unstable, and neutral equilibrium. So we say that a body with a large base and low center of gravity is stable, while a body with a small base and low center of gravity is unstable. You also know that when the center of gravity is high, the potential energy will be high. Therefore, the body will be unstable. But when the center of gravity is low, the potential energy will be low. Therefore, the body will be stable. Okay, your assignment. Number 1, you state the condition for the equilibrium of a number of non-parallel coplanar forces. Then number 2, define center of gravity and describe how to find the center of gravity of irregular piece of aluminum sheet. Number 3, state the effect of center of gravity on the stability of a body. Number 4, list 3 types of equilibrium and give 2 examples of each. So you do the assignment and submit in Google Classroom. So any question can be forwarded to the Google Classroom, or you bring them up in our Zoom class. Thank you very much for listening and stay safe.